I want to cover some module and system level issues today, and I want to cover them today because next week we have a guest speaker on that topic, and also this would be something which would be useful while you're doing your project. Okay, so I'll cover mostly these two things: the module and system level issues, and then talk about microinverter. This thing I'll limit to light conversion, limit to light concentration is something I'll just put it in the videos. Okay, so actually let me ask you. So what do you think is the temperature at which a normal cell operates? A solar cell, a solar panel. Usually, if you like put it out right now, where it's 70 Fahrenheit or 25 degrees centigrade, what would be the temperature of the panel? 60 feet. 40. Okay. So, if you think about the panel, it's actually a very bad system for heat conduction. You have these cells, silicon, silicon is not the best conductor, but compared to what it's surrounded with, it seems its conductivity seems very high because it's surrounded by this EVA polymer, and then on the back mostly you have this white sheet of Tedlar, which is also a polymer material, and both of them are poor conductors of heat. And on the top you put this glass, which is also a very poor conductor of heat. So this solar, whatever generation, heat is, the energy which is coming in, it's very hard for it to get out. Whatever heat is being generated, it's very hard for it to get out. So there's kind of a greenhouse effect, plus all the generation recombination which is the recombination which is happening in the cell. It's hard for it to escape out. So the temperature depends upon your irradiance level. So typically you have irradiance level of 800 watt per meter square, which is equivalent to 80 milliwatt per centimeter square. So if you have a panel which is encapsulated in gas, it would go up to a temperature of approximately 40 degrees C. You can reduce it. There are many ways you can reduce it. You can place aluminum foil behind your panel. So you can, instead of mounting it on this plastic, you can mount it on a metal, but you'll have to make sure that you don't end up shorting with that metal. That's the thing you'll have to take care into. But if you do that, you can in fact reduce it. Other thing which can help you is like if there's a good wind flowing. So there's some there could be either conductive flow of heat or convective flow of heat, and the presence of wind helps in cooling your panel as well. So, but on a typical day, like a day like today, if you place a panel outside, which is at an ambient of 25 C, your panel will operate at 40 C. If you have most of these multi-junction cells, they operate even higher. They operate at when you put concentration of light, you do get the advantage that you're not surrounding it by glass. You are surrounding it by this heat sink at the back, just like you put at the back of a Pentium processor. It's that same heat sink, that intermeshed aluminum foils which you put at the back, but it operates anywhere between 60 to 190 C, depending upon what is the concentration you're looking at. Okay, so we talked about this a little bit earlier, but I want you to consider it again. So let's say I have two cells. I have these two of my cells, and one of them has some problem. So this black guy is my bad cell. So I have a good cell which has an IV characteristics like this. It has a high open circuit voltage, and then I have a bad cell which has less current and also less open circuit voltage. Okay, so now when I connect them together, and this is showing for the case where they are connected in parallel. Okay, so the combined current of the total would essentially be sum of the current of the individual two, right? Because they are connected in parallel. But what about the open circuit voltage, right? So one guy clearly has much lower open circuit voltage as compared to the other guy, right? So the open circuit voltage of the overall cell, as you can see in this picture, it lies somewhere in between, where it lies in between the first cell and the second cell. And the best way to understand it is, look at what individual cells are trying to do. So this guy clearly wants to achieve, the cell number, let me actually label. So the cell number 1 wants to achieve a high open circuit voltage, right? So what it will do to do that is essentially, it will try to push the IV of this bad cell towards the right? So it wants to achieve a high open circuit voltage. So it's going to pull the other thing towards the right, especially when you're nearing the open circuit voltage condition. So it will essentially, try to bias this other cell in a way that it tries to become a consumer of electricity instead of a producer of electricity. So it's trying to bias this thing in this regime where it's no longer producing power, right? Especially when you're trying to reach this open circuit condition. So, these two IVs, essentially, the presence of this good cell is trying to push the IV of this other cells towards the right. And so overall, you get a VOC which is somewhere in between. So you get an open circuit voltage which is in between the two. And when that open circuit condition happens, actually one of the cell is producing power and the other one is consuming power. Right? So a quick hack to understand it, what happens if you have one good cell and one bad cell connected in parallel, is to essentially think of this bad cell and flip its IV, right? So now what the first cell is trying to do is trying to push this second cell towards the right. So it's going to try to bias this other cell in this regime where it, instead of producing power, it consumes power, and it is going to be able to do that until a point where these two curves meet, and that would be the overall VOC of your combination. So you could do the same exercise. You can model these diodes in SPICE and see that if you have a bad diode and a good diode, the overall open circuit voltage you will get is somewhere in between the two. But this is a quick hack to try to understand it, where what will happen if you have a good cell and a bad cell. If they are connected in parallel, you can flip one of them, the bad cell, and see what is the overall open circuit voltage you get. Now, the more important is what happens when you have these mismatched cells in series. Okay, so this is the case now, and I'm invoking a little bit of circuit theory, but I don't want to go too much in detail. Just understand it very intuitively what's happening. So again, I have a good cell. So my good cell has a IV characteristics which is like this. Okay, so it has very high current and it has a certain voltage. And then I have a bad cell which has a low current, right? And it has a slightly less open circuit voltage as well, right? So now what will happen if I essentially, if I connect them in series? So if I connect them in series, my combined output, it essentially will have, the open circuit voltage will approximately be the sum of the open circuit voltage of these two cells. But what about the short circuit current? So what about this short circuit current? So again, what the first cell over here, the good cell, is trying to do is it's trying to push up this current of the bad cell, especially when I'm reaching this short circuit condition. So what it's trying to do is essentially it's trying to pull up the current of the bad cell. So it's essentially going to traverse along this direction, and it's probably going to bias it till this point where it's trying to bias it in the reverse bias regime. So in fact, in the short circuit, when you're approaching the short circuit condition of this overall module which has these two cells, one of your cell would be forward biased, it would be producing power, while the other cell would be pushed in this regime where it's reverse biased. Okay. So again, a quick hack to understand it is to take the bad cell and reverse flip it over on the y-axis. So a quick hack to understand what would be your overall short circuit current is take your bad cell and flip it over. And so the first cell, the good cell, will essentially try to bias it in the reverse regime, and it's going to able to do that until these two curves intersect. And this would be your overall short circuit current, overall JSC of your overall module, which is consisting of this one good cell and one bad cell. So it's always the good guy. He's trying to trying to bias the bad guy, and it will if it's connected in series, you flip it on the voltage on the y-axis to understand it. If it's connected in parallel, you flip it on the x-axis to understand it. Okay. So now let's consider the case of many strings of these cells connected in series, right? So this is, say, one bad cell. Something happened to it. It cracked. A bird pooped on it, or something, right? So these are your good cells, and this is the combined output of these good cells. So your VOCs have added up. So this is all your good cells. Now this is my bad cell, and this has a IV characteristic which is like this. So instead of going all the way, it essentially becomes like it becomes reverse bias. Usually you have a very flat reverse bias, but I'm showing over here it's like more like a reverse bias increasing as a reverse current increasing as a function of bias. So again, what would be the overall short circuit current over here? So I essentially flip one of my combinations. So I flip this good cells on my y-axis, and then I take an intersection of this with the bad cell, and that would be my overall JSC. So this is my overall short circuit current, and my overall characteristic would look something like this. So you can see, as compared to the ideal case, I am producing much lower power, and so where's that extra power is being dissipated? Where is being dissipated? Bad cell is forward bias or reverse bias? Yeah, it's reverse bias. So that's the point I want to make clear. Let me explain it again over. So whenever you're approaching over here, right, you are trying to push this bad cell into a reverse bias condition. So this bad cell is now in a reverse bias condition, and the worst case would be essentially if you just connect them and short the overall loop. So these four cells are producing the power, and since that power can go nowhere, this bad cell is is going to dissipate all that power, and as a result of that, it's going to become very hot. And this is something I encourage you to experiment when you're making your module. Just cover one of your cells with just cover it with hand and see, it will become hot very quickly, because it will become reverse biased, and it will start dissipating a lot of heat. Okay, so the solution to this is something we already mentioned earlier, is to connect a bypass diode. So let's say this cell is a PN junction in this direction. Okay, so or should it be a PN junction in this direction? So should this bypass diode should be in the same polarity as the cell, or should be in the opposite polarity as the cell? What do you guys think? How many people think same polarity? Same polarity and opposite polarity? Is there a reason you think same polarity? Now I'm saying the okay, maybe let me clear. So the cell has a certain polarity, right? The cell is also a PN junction, right? So now let's say I have this cell which is a PN diode like this. So should I connect the bypass diode like this, or should I connect the bypass diode like this? So, I mean, if it's okay, it might be a while since you studied diodes and circuits. So, the each of this cell, right? So this is my bad cell. So it has the lower, it has this bad characteristics, right? So typically my good cells, they would want to bias my bad cell in the reverse direction. Right? So if I connect a diode which is in opposite polarity, so if I essentially connect a diode which has a polarity like this, so this is my cell and this is my bypass cell. So when the other good cells are trying to bias this bad cell in a reverse condition, this bypass diode will turn on, right? It will become forward bias and it will turn on. And instead of this IV remaining flat, it essentially becomes like this, where the combined thing has an IV characteristic like this. So if you try to reverse bias it, the bypass diode will turn on, and it can conduct the current instead of that current being flowing through this reverse bias cell. So if you have this n good cells and you have this one bad cell with the bypass diode, your overall characteristics would look something like this. But instead of all that power being lost, you will now dissipate less amount of power, because you have reduced your overall fill factor much less, and part of that power will be dissipated in the bad cell, and part of it will be dissipated in this diode. Okay, so you want to engineer this bypass diode such that its knee voltage, or its forward bias voltage, is such that it's positioned to the point where you want it to get turned on. Okay. So this is how it's done, right? So you typically take a bunch of these diodes which are connected in series, because it's very expensive to have a bypass diode for each individual cell. So you draw the line somewhere. You say, okay, I can tolerate if I have 72 cells in series, maybe I'll put 3-4 bypass diodes. So if something wrong happens, output of my panel will drop by 1/3, or depending upon how many bypass diodes you put. If one cell goes wrong, accordingly that string will get shorted. Okay, so if something wrong happens in this series, so in this series I have these diodes connected like this. So I have 4 of these PN solar cells. Okay. And if this guy goes bad, so these guys are still producing current, right? But that current is now instead of producing power, that power will essentially just get dissipated in this forward bias bypass diode, and part of it will get dissipated in this reverse bias cell as well. Okay, so you usually put your bypass diodes on the short side of your panel. So suppose your panel is a rectangular shape like this. So you usually put a few of them on the short side of the panel, and you usually connect 2 or 3, or depending upon how much loss you want to tolerate, and put a bypass diode over here. So keep that in mind. I'll ask you a question about this later.